Hey, welcome back. This is Trig 4.8 applications. You may want to pause the video and get your book open at this point. We're going to be looking at some story problems here eventually. And if you open it up around page 637, you should be on track if you want. I'll try to be as comprehensive as possible though. So anyways, solving right triangles will be our first mission. And again, page 637 is where the homework starts. The directions: solve the right triangle. That's supposed to be a V. Solve the right triangle. And all that means is to basically fill out the unknowns. So there's going to be three angles and then three sides. Clearly this angle is known to be 90 degrees, but you're going to label the angles A and then B and then C going, I guess that's clockwise, starting with A on the bottom here. And then the sides will be lowercase letters. So the side opposite angle A will be lowercase a. The side opposite angle C will be lowercase c, and the side opposite angle B will be lowercase b. Okay. Okay, so we need to figure out those pieces, so how do those problems go? So number 2 in particular, we have given information, and then we kind of have to figure out the rest from the given information. So make sure your calculator's in degree mode for these kind of problems. Okay. So let's kind of draw the triangle and see what we have. So A, B, C. So this little b is 20. We don't know little c, and we don't know little a. And this angle here, this one is 90 degrees. It's always going to be 90 degrees. This one is 41.5 degrees. Okay. So the first thing you could do is the low-hanging fruit, so to speak, is this angle B. And you can get that easily because the three interior angles of any triangle have to equal 180 degrees. So basically you just take 180 and subtract away the angles you know. So 41.5 and also subtract away 90. And you'll end up with, if you get your calculator out, 48.5 degrees. Okay, so we can fill that in. And we just need to figure out A and C. So usually I like using the tan function to get my answers. So here I'm going to try to get A, right? So the tan of the 41.5 degrees, tan of 41.5 degrees is equal to opposite, which is this A that I don't know, all over adjacent, which is B, which I do know is 20. And then you can solve this for A. Right, you can just multiply both sides by 20, and you have an expression for your answer. A is going to be 20 tan of 41.5 degrees. 41.5 degrees. And if you put that into your calculator, assuming you're in degree mode, let me make that look a little prettier for you. So 41.5. And assuming you're in degree mode, you should get 17.69 degrees. Or sorry, this is a length, so this will be 17.69 units, whatever the units are. I don't think they specify the units here, though. Okay. Then thirdly, you don't have to really do any more trig. Once you get two of the sides, you can use the Pythagorean Theorem to get the third side. So c squared, the hypotenuse squared, will be just the 17.69. And the book tells you how many decimals to approximate to. So they wanted 1 decimal on the degrees and 2 decimals on the length. Okay, so it would be 17.69 squared plus 20 squared. And then you take the square root on both sides, and you get 17.69 squared, whatever that is, plus 20 squared, and then you drop that into your calculator, and I got earlier 26.70 for my approximation to 2 decimals. Okay, and then you've kind of completed the triangle, or you've solved the triangle, so to speak. Okay, and that's the idea, and all these problems are just basic variations on this theme that give you different information. You have to track down the unknowns. Okay, so let's try another. A is the distance 11.2 units, and C is the distance 65.8 units. Let's get our triangle set up. Okay, so angle A, B, C. A is 11.2 and C is 65.8, and we don't know B. Okay. So what do I need? I need angle A, angle B, and side little b. Okay. So, rather than using A, B, and I got so many A, B, and C's floating around. Let's go 1, 2, and 3. Right. So first off, I'm going to get side B, and you can get side B using Pythagorean Theorem, right? So just note A squared plus B squared is equal to C squared, and solving for B, you get B squared equals C squared minus A squared, so B will equal the square root of, and then I'm going to substitute in the values, so 65.8 squared minus 11.2 squared, and then evaluate that curve, and you end up with, according to my calculator earlier, 64.84 to 2 decimals. Okay. Okay. So where is that? That's B, 64.84. Okay. Step 2. Now I'm going to go after angle A, this angle down in the corner. And I'm going to note that the tan of this angle A, so I'm not getting carried away with sines, cosines, cosecants. I strictly just kind of try to use tangent. Okay. So tan of angle A is opposite, which is our A value, which in this case is 11.2, all over adjacent, which is the little b value, which is 64.84. Okay. To figure out A, then you just do tan inverse on both sides, and you end up with A equaling tan inverse of 11.2 all over 64.84. I'm going to have to go to my calculator for this one. So make sure you're in degrees. I'm going to make sure I'm in degrees. Okay, good. And we're doing tan inverse 11.2 divided by 64.84. And I'm getting 9.8 blah, blah, blah to 1 decimal place. I need 9.8 degrees. Let's make sure that's correct as far as the round lengths to 2 decimal places, angles to the nearest tenth. So we are good. So after I get angle A at 9.8 degrees, I can easily get angle B just by using that 180 degree property, right? So angle B will equal 180 minus 90 degrees with the C angle minus the 9.8 degrees, which is the A angle. And if you subtract those together, you'll get 80.2 degrees, which finally solves our triangle. Okay. Okay. Let me make sure I'm recording. Okay, everything seems normal. Let's move on. Okay. So the next section, I entitle it Height, Distance, and Angles. These are kind of applications. Height, distance, and angles. Yeah, I don't remember if I mentioned it, but if this is the horizontal, like that, maybe you're looking out in the distance and you see the horizon, think of it like that. An angle that goes above the horizon is called an angle of elevation. Okay, and that comes up in some of the applications. You need to know what that is. Angle of elevation. If you go below the horizon and you have an angle like this, that angle is called the angle of depression. So a lot of my so you just have to know those kind of phrases. I don't know if those are standard or whatever, but anyways, let's look at a story problem here. So we have problem 41, trying to figure out the height of a tower, television tower. So the tallest television transmitting tower in the world is in North Dakota. From a point on the ground, 5,280 feet from the base of the tower. So we have this big tower thing. I don't know if it's a cell phone tower. Those kind of look like this. But anyways, from the base of there, and they said it's 5,280 feet, which is 1 mile, 280 feet. From the base of the pole, the angle of elevation is 21.3 degrees. Okay, so it says from the point on level ground, 5,280 feet from the base of the tower, so they're talking about this point here, the angle of elevation is 21.3 degrees. So if you kind of created a triangle, that angle of elevation is this angle right here is what they're talking about. And then that will be 21.3 degrees. Their question is to then approximate the height of the tower to the nearest foot. Okay, so they want to know then this height to the nearest foot. Okay. Again, that seems like I can pull off a tangent. So I just noticed the tangent of 21.3 degrees is equal to opposite over adjacent. Multiply both sides by the adjacent side, and you should have your answer, right? So x is equal to 5280 tangent of 21.3. Let's put that into our calculators and get an approximation to the nearest foot. And 3. So, geez, it's a half a mile tall. That is ridiculous. So it's 2,059 feet tall. Under a half mile, but it's still really tall, right? Okay, let's look at another one. This is 48 in the book. And what do we got? A building that is 200 feet high. So we have a building this time. It is 250 feet high. Casts a shadow 40 feet long. So I'll pretend the sun is over here. And we're casting a shadow 40 feet long. Find the angle of elevation again to the nearest tenth of a degree of the sun at this time. So you can assume that the angle of elevation to the sun is found in that way, where this is your angle, okay, that we're after. So let's just call it something, call it theta. And again, it looks like we can use the tangent function. So basically, we're going to say the tan of theta is equal to opposite, 250, all over adjacent, which in this case was 40. Okay. And then do tan inverse on both sides, and you end up with theta equaling tan inverse of reducing a little bit, 25 fourths. And then we go to our calculator. Tan inverse of 25 fourths is 80.9 something. What decimal place do we need? Nearest tenth. So we are looking at 80.9 degrees. Okay. It's pretty easy. This next set of problem, we have kind of multiple right triangles spliced together, and they turn into kind of story problems where you have to use maybe sometimes some creative thinking. But anyways, let's take a look. So multiple right triangles. And the first one, number 30. Let's take a look. So we have our first right triangle like this, and then they put another right triangle on the bottom of it. So probably not completely accurate. But this is a right triangle. This is a right triangle below it. They tell you this this distance here is 100 on both triangles, that length. This angle is 20 degrees. This angle is 8 degrees. And what do they want to know? They want to know this distance. Okay. Okay. So I think the way, again, you're going to have to kind of be creative and play around with this a little bit, but ultimately the solution that I fell onto was to figure out this length, okay, and then figure out this length, which I'll call B, and then just add them together, and that's equal to x. Right? So x is equal to a plus b. So you kind of cut it into two smaller sub-problems. Okay. Each one is based off a right triangle. Okay. So anyways, again, I could probably get away with the tangent. The tan of 20 degrees for the first right triangle, the top triangle, will be equal to opposite, which is just little a, all over adjacent, which is 100. Okay, so if I multiply both sides by 100, you end up with a equaling 100 tan of 20. Okay. Then, for the second triangle, I can use tangent again. So I'll just say tan of 8 degrees is equal to opposite, which in this case is b, all over adjacent, which is 100. And then again, I can solve for b, and I get 100 tan of 8 for b. So ultimately then x is just going to be 100 tan of 20a plus 100 tan of 8b. And then you just go to your calculator and get that. Okay, so I'm going to get my calculator here. 100 tan of 20 plus 100 tan of 8 is 50.45, depending on what decimal place. Let's see what they want. Nearest whole unit, so they just want 50 degrees. Or sorry, it's a length, so 50 length units, whatever the lengths are. Okay. Okay, let's look at another one. And this next one is going to be your video quiz question, so all you have to do is pretty much just copy it and put it in your notes. Okay, so this is the video quiz. Let's take a look. So we have this double triangle, one inside the other. Okay. They're telling us this angle is 48 degrees. They're telling us this angle is 20 degrees. And they're telling us this side is 500. And they want to know this value of x. Okay. Okay, so again, I'm going to kind of cut it into two sub-problems, and my solution will be based on those sub-problems. So I figure x is the difference between two lengths, right? X is this length minus this length. And those lengths are just the bases of these two triangles, these two right triangles. And I have a feeling that I can kind of figure those out just using tangents, right? So first off, the tan of 20 is going to equal opposite, which is 500, all over adjacent, which in this case is that big A, right? The long A here. You can solve for A, so multiply both sides by A, and you get A tan 20 equals 500. And then you can divide both sides by tan 20. So you get A is 500 over tan 20. Okay. Then do the same thing for B, so you use the smaller triangle. So for the first part, I used this blue triangle, right? And then for the second part, I'm going to use this smaller triangle here, this red triangle. Okay. So for the red triangle, I say, okay, tan of 48 degrees must equal opposite, 500, all over adjacent, which I just called B. Right? And then again, you could solve for B, so multiply both sides by B. You get B tan 48 equals 500. And then divide both sides by tan 48. Okay, and that's really it, right? Because x is just equal to a minus b. So a we found to be 500 over tan 20. And then minus b, which is 500 over tan 48. Okay. So plop that into your calculator, and they want the nearest whole number. So let's see, we got 500 divided by, get a little practice using your calculator. You'll need to be able to use it on a test, right? So you might as well get practice with it. Tan 48. Okay, you can't use graphing calculators on the test. You can use like a scientific, but no graphing calculators. Okay, so to the nearest whole number, it would be 924 units. Okay. Okay. The next thing we want to talk about bearings. So this is used in navigation and in doing surveys. So it's kind of a weird directional system. Airplanes kind of have a weird directional system too, with regards to the XY plane. They always do angles, I think, from the north, and then they wrap around, so that tells you the heading of the plane. But bearings, navigation, and then like with boats, and then doing surveying. So the way this works is you're going to start at either north or south. So in the XY plane, this is north, this is south, this is east, and this is west. So start at north or south. And then you kind of open up your angle away from the north or away from the south. Okay. And you're going to use the acute angle in the direction of the terminal side. And that'll be more clear once we look at some examples. So use the acute angle. Again, acute angle is less than 90 degrees in the direction of the terminal side, which is basically just the direction the boat is going in. Okay, so let's look at some examples. This is 13 in the book, and we set up our XY plane and sort of label the axes. This is north, south, east, west, and we want to know the bearing for going from O to A is the way the book will kind of say it. Okay, and they give you this angle here, 75 degrees. Let me make sure the question is. So it says, use the figure shown to solve the question, and the question says, find the bearing from O to A. Okay, so that line there is the terminal side, and the way you talk about bearings is going down from north. So the actual angle we're concerned with is going to be this angle, and it's in the direction of east. So the first thing, there's going to be three things. The first thing is either north or south, and we're coming down from north, so we start with N. You write big N. Okay? And then the middle, you're going to put the acute angle, that red angle that I just drew, the angle down from north. So in this case, it's you figure it out by going 90 minus 75, right? The overall angle from north to east is 90 degrees, and then if you take away the 75 degrees, you get angle A. So 70, 80, it's just 15 degrees, right? Okay, so the second thing then is that angle. You put 15 degrees, and then you put either east or west. So in our case, we went towards the east. So the bearing is north 15 degrees east. Okay, let's look at another one. So this is 15. Okay, and this problem, we want to find the bearing from O to C, where again, O is right here, and then C is right here, and they give us the angle, this time the angle that we want, 80 degrees. Okay, so again, this is north, east, south, west. So the first thing you write is, we're coming down from the south. Okay, So if it's in the first or second quadrant, you're going to start at north. If it's in the third or fourth quadrant, you start with south. Okay. Then you need the angle coming down from that axis, the negative y-axis. You need this angle right here. Okay. And they've been nice enough to give that to us. It's 80 degrees. Okay. And then we went in the direction of west. So actually we went south 80 degrees west. Hopefully that's kind of clear. Let's look at maybe an exercise. Hopefully that will put us on more sound footing. This is 52 in the book. So it says a boat leaves the entrance to a harbor and travels 40 miles on a bearing south 64 degrees east. Okay, so let's kind of draw a picture. That's always a good way to start. So here we have north. Here's south, here's east, here's west, and it says we're starting with south 64 degrees east. So your initial side is the south, going in the south, and then you're rotating 64 degrees to the east. Okay. And there's my terminal side. Okay. It says the boat leaves the entrance to a harbor and travels 40 miles on a bearing of south 64 degrees east. So basically, if you think of going from O to some point A on that terminal side, so the origin to maybe call this A, that length of that leg of the distance, leg of the, I don't know, journey is 40 miles. Okay, so you're going to put a 40 right there. They want to know then how many miles east from the harbor has the boat, how many miles north and how many miles east of the harbor has the boat traveled. So the harbor is that O. The harbor is the origin. And then the two values that we're after are basically just the x and y coordinates of that point A. So the amount south is the y coordinate, this red distance here. And then the amount east is the x coordinate. So that would be this distance here. Okay. Which is also this distance here. So the red is the distance south, and the yellow is the distance east. Okay. Okay. Then we could use a right triangle, I guess, to solve this. So there's my right triangle, and here's my angle. This time I don't really know the opposite or the adjacent, so I may have to use like a different trig functions. So it looks like maybe I'll have to do two of them, right? So I know that cosine of 64 will be adjacent, which will be that red distance I'm after, right? So it's going to be this I'll just call it y. So it'd be the adjacent all over the hypotenuse, which is giving us 40. Okay? So we can solve for y by multiplying both sides by 40, and you're going to get the red distance, which is the distance south. Okay, so put that in your calculator. 40 times cosine of 64. And I don't know what approximation they want. What is this, 52? Doesn't really tell you what approximation they want. I'll just go the one decimal. So this is 17.5 miles. And we traveled south. Okay. And then for the yellow, we can use sine, right? So sine of 64 is going to be opposite, which is, let's call that x, the yellow, all over hypotenuse 40, right? So again, you just solve for x, multiply both sides by 40, get 40 sine of 64. Okay, so 40 Sine of 64 is 35.95, so rate rounding 36.0 miles east. Okay. Okay. Let's move on to something else, maybe vaguely more interesting. Simple harmonic motion, which is a big topic once you get to something called differential equations. And I'm sure it's big in physics as well. It's been like 20 years since I've taken physics though, so they don't know what they're doing that much anymore over there in that universe, but there it is. Okay, so anyways, simple harmonic motion. What we're thinking of is kind of a weight on a spring. And there's all kinds of different ways to orient this. Sometimes they draw the picture sideways, but there's going to be some equilibrium position. So we'll call 0 that point, the equilibrium position. Equilibrium position. And then there's some sort of displacement going up and down. So if you, okay, so the picture, we have this weight attached to the ceiling, or in other orientations you can think of it as a wall or something like that, and somebody comes along and pulls on the weight, pulls it out of equilibrium. Okay, so we'll make this negative down this direction, but you can kind of position it however you want. So somebody is going to kind of move it out of the way and then let go, and it's going to go back and forth, right? So the overall effect, if you were to kind of time lapse it, or you have like a, I don't know, one of those cameras that takes pictures every 2 seconds or something like that, what you're going to end up seeing is this phenomena as it travels back and forth. And the point is that the end result of this spring action is, guess what? What kind of curve does that make? Well, I think you can guess. Okay, so the spring is now coming back up a little bit. And it's at equilibrium position. And then it's kind of smooshing back up. And now it's really smooshed up. Right? And then it starts stretching back out. Okay, so again, you know, what? So what? Well, look at the graph. It's one of these. Well, in this case, it looks like it's a upside down sine curve with a shifted phase. But yeah, simple harmonic motion. We can model this phenomena with sine and cosine. So in particular, our formulas, our mathematical models for simple harmonic motion at this point will be displacement d equals the amplitude a times cosine of omega times t. Okay. So, or you can use the sine version, which would be a sine of omega t. So that weird curly looking w thing is an omega, a lowercase omega. Okay. Okay. So again, you know, what is d? D is displacement. And so displacement from rest positions. So you can, you know, the rest position is at 0, and then the displacement here is a little, you know, it's like -2, and then maybe it's -4 down here. What else is there? A is the amplitude, and of course we want absolute value, right? So amplitude. Very quickly, you can figure out the period, you know, working with our usual interval from 0 to 2 pi, and just divide by omega. So our period is 2 pi over omega. And we're also going to start worrying about something called frequency, which is just the number of cycles per time unit. Frequency is the reciprocal of the period. So it's 1 over the period, which is equal to then omega all over 2 pi, and the units are in cycles per whatever time unit. So like cycles per second, we'll say something like that, okay? Okay, so, you know, a cycle, this is one full cycle right here. So remember, a cycle is basically just like one period. Okay, it's that kind of same thing. Okay, so let's take a look maybe at like a checkpoint time kind of problem. So checkpoint, what do we have here? This is checkpoint 7, apparently. Let me see what it says. So checkpoint 7. A ball on a spring is pulled 6 inches below its rest position and then released. Okay, so you can kind of sketch it out. 1, 2, 3, 4, 5, 6 units away from its rest position and then released, and its period of motion is every 4 seconds. So 1, 2, 3, 4. So, you know, as you release it, it's going to go back to the middle, and then up top, and then back down, and we're getting the cosine form. Okay, so it looks like 1 cosine, and it looks like it's upside down, right? So you're going to have to make it negative. So write the equation for the ball's simple harmonic motion. So in this case, the absolute value of the amplitude looks like it's 6. Our formula then is going to be some version of -6 cosine of omega t, and then I kind of have to figure out what omega is. So the period we know is 4, and the formula for period from above is 2 pi over omega. So we can solve for omega by multiplying both sides by omega, and then dividing both sides by 4. Right? So you get 2 pi equals 4 omega, and then divide by omega by 4, and you get omega equals pi over 2. And then you just stuff that back in here, and you have your equation. Okay? So y equals -6 cosine of pi over 2t. Right? Okay. Did I give you the video quiz problem? Did we do that? Yeah, I did. All right, so checkpoint 8. Let's check. Oh, we still have to. We're not done. They also want the frequency. Okay. Well, maybe they don't want the frequency, but the frequency is easy. It's just omega over 2 pi. So the frequency is pi over 2 all over 2 pi. So that's pi over 2 times 1 over 2 pi, which is 1 all over 4. If you remember, every 4 seconds you have a period. So there's 1 cycle every 4 seconds is how you would read that. 1 cycle. 1/4, or in other words, 1/4 cycle per second. And then in 4 seconds, you'll have 1 complete cycle. Okay, let's look at checkpoint 8. Okay. So checkpoint 8, and see how that goes. An object moves in simple harmonic motion described by the displacement formula d equals 12 cosine of pi over 4t. Part A. And also t is in seconds, and d is in centimeters. Okay, part A, find the maximum displacement. Well, that's easy. That's just the amplitude. So that's 12 centimeters. Part B, the frequency. Well, that's 1 all over the period. Okay, so the period is, so, well, we could just read omega off, right? So omega is pi over 4. The period is 2 pi divided by omega. So in this case, it's 2 pi times 4 over pi, just doing the reciprocals. And then what you get is 8. So again, what do they want to know? the frequency. So the frequency is just the reciprocal of that, so 1 all over 8 cycles per second. Or centimeter, cycles per second. Yeah. Part C, to find the time required for one complete cycle. Well, that's just going to be 8 seconds, right? Because if you have 1/8 of a cycle per second, then you're dealing with 1/8 of a cycle per second. You need 8 seconds to get the full cycle, all 8 parts, right? Did they ask for period? Doesn't seem like they asked for period, so we'll leave it at that. Let's maybe look at some of our Mymathlab materials. So where are those going to be found? Google. The Google platform here. Just bear with me 1 second and I will get it. Okay, so the first 7 or so problems are just solve the triangle, and then there's like 2 bearing problems, right north 15 degrees west or whatever. This looks like a displacement problem, so this is now, we're in 4.8. An object is attached to a coiled spring. The object is pulled down from the negative direction 7 centimeters and then released. So it's starting here. Write an equation for the distance d of the object from its rest position. After 2 seconds, if the amplitude is 7 centimeters, clearly, and the period is 3 seconds. So 2 pi over omega is 3 seconds. So I need the equation for this. Because it's starting downwards here in the negative direction, it's going to be a negative cosine item. So it's negative 7 cosine of omega. So solve this equation for omega, and you get 2 pi over 3 equals omega. So just doing that quickly in my head. 2 pi over 3, and then I guess they want t for seconds. And let's see, negative 7 cosine of 2 / pi over 3, boom, t, end parentheses. Oh, you got to write y equals probably. Y equals, oh, what did I do? I have no idea. I can only assume they want D. Is that the deal? Yeah, okay, so you need to put D in there instead of Y. Okay, what else? Object begins at the rest position at 0 seconds, so it's right here. And then it's propelled downwards, so it's going to go down like this, and then back up, and then back down. So this is going to be a negative sign. So its amplitude is 5, so it's going to be negative 5 sine of something. And so we need the omega value. Period is 4, so 2 pi over omega is 4. So it's going to be 2 pi over 4, so omega, and then that'll just be pi over 2. So pi over 2t. And remember to use the appropriate variables this time. D is negative 5 sine of backslash pi over 2, and then t. An object moves in simple harmonic motion described by the equation D equals 7 cosine of 2 pi t. Find the maximum displacement, so that's just 7, the amplitude. Okay. Find cycles per second, so that's a frequency, which is going to be omega over 2 pi. In this case, omega is 2 pi, so that will just be 1 cycles per second. And what's part C? Find the time required for, well, 1. 2 oligers. Okay. Next, the object moves in simple harmonic motion. Distance is 1/4 sine of 2t, where, okay, so find the maximum displacement. Again, that's just 1/4. Yay. Find the frequency. So that's just going to be, again, omega, which in this case is 2 over 2 pi. So in our case, it's 1 over pi. 1 divided by p. Answer. Find the time required for 1 complete cycle. So the frequency is in cycles per second. So I find the time for 1 cycle. You need pi seconds. It's just pi. Sorry, there's a bug on my screen. You can't see it, but I can. What next? Ugh, is this the same problem? Frequency, and yeah, it's the same. I'll do this one more. So hopefully it'll change to something else. 4 sine of 2 pi over 5t. Maximum displacement is 4 inches, not -4. The frequency, is omega over 2 pi. So omega is 2 pi over 5. So times 1 over 2 pi, then multiplied by the reciprocal of 2 pi. 2 pi's cancel, so that's 1/5. So 1/5 of a cycle per second. So it's going to take 5 seconds for that thing to pan out for part C. Oh, this is a double triangle problem. Leave that one. I did one just like that in the lecture. It's another double triangle problem. Again, I think my lecture kind of handles that. I think this one was harder for some reason. Let's take a look at this one. Okay. They want you to find this distance, which is x, and they're giving you, this is 50 degrees, this is 25 degrees, they're telling you this is 420, and that's about it. Right? So there's kind of, again, 2 different bases here. There's A, and then there's base B. But then you have like this extra variable. So that's kind of the bummer part. So just notice here that we can rewrite A in terms of B. So B is actually equal to A minus 420. Okay, so maybe that'll help us. So let's take a look anyways. So tan of 25 is going to be opposite over adjacent. So the big long side is A. Okay, so x will equal A tan of 25, which seems like a lost cause because there's 2 variables, but let's see what happens. Okay. This other part, tan of, I guess it's a 50 degree, is equal to opposite, which is again is x, all over the adjacent side, which is b, but we can rewrite b as a minus 420, right? And then we can go ahead and solve for x again. So x is equal to a minus 420 times tan of 50. Okay. Notice that x has 2 expressions here, and so you can do a substitution. In other words, set those 2 equal to each other. So you have a tan of 25 equals a minus 420 tan of 50. And then hopefully you could solve for a here. So a tan of 25, distribute this tan, you get a tan of 50 minus 420 tan of 50, and then move this tan over here, move the 420 over here. I'm just kind of avoiding the negatives, right? So I have the end there, a tan 50 minus a tan 25 equals 420 tan of 50. Factor out the a, so you get tan of 50 minus tan of 25 equals 420 tan of 50. Okay. And then divide both sides. So yeah, that one was a little more complicated. 420 all over tan of 50 minus tan of 25. So let me get the value for that. 420 times tan of 50 divided by tan of 50 minus tan of 25. Make sure you put the entire denominator in do not round final answer. Do not round until the final answer. Okay. So this is about 689.971-ish. And then I guess we can get, did we find A? Yeah, we found A, and then to find X, you could just plop it into this formula, I guess. So X is equal to A tan 25. So just multiply that answer you got times tan of 25, and you should be good. Is there an easier way to do this problem? I don't know. Off the top of my head, this is what came to my brain. So 322 rounded to the nearest whole number. So I apologize if maybe there's an easier way, but that got the job done, so let's just leave it at that. Okay, object moves, simple harmonic motion, blah, blah, blah. T is measured in seconds, D is in inches. Answer A through E. So what's the maximum displacement? So clearly that's 3. It's just the amplitude. What's the frequency? So here it's a little more complicated, right? So it's pi over 2t plus, there's kind of like that shift going on. There's a period shift. So 0. Or a phase shift, not period shift. Okay, so I'm going to minus pi over 2 from all three sides. And then multiply everything by 2 over pi. And so you get -1. 2. Whoops, I forgot to minus pi over 2 here. Multiplying by 2 over pi on all this junk. Right, so everything got multiplied by 2 over pi. The first distribution, you'll have 4. And then the second distribution, you just have 1. So the period is 4. Is 4. And so remember, the period is just 2 pi over omega, which in this case is 4. So that tells me my omega, if you multiply both sides by omega and divide both sides by 4, is just going to be pi over 2. So, you know, what is the frequency? The frequency is 1 over the period, so maybe I just did some overkill there, but the frequency is 1 over 4, right? It's 1 over the period. Sorry, carried away. Clearly 4 seconds then is required for 1 full cycle. And then the phase shift is just -1. Oh, geez, this question just keeps on giving, huh? So what does it look like, basically? It's a cosine form. I'm not saying it. All these are upside down, so these are all like negatives. Is there another one? I'm not saying. Oh, because it's phase shifted. Okay. So it should start at negative pi over 2, or it should start at negative 1, sorry. And then, so I hate these little, I'm just basically going to have to draw it out and then kind of match it up. It's the long way. Sometimes you just got to go brute force, you know. So, what do we got? So it's negative 1, and then the period we said was 4, so it's going by ones, and it's a cosine. So it's up there, then down here, then down here, and then back up here, and then at 2, so it's 3, 4, should look like that, and 4, 5 should be back down. So find the one that goes back down at 5. Make sure you get the amplitude to be 3. 1, 2, 3. 1, 2, 3, 4. Nope. 1, 2. That's definitely not it. 1, 2, 3. That's not it. And then, so the process elimination, this has to be it. Okay, so 1, 2, 3, 4. That don't look right either. It has to go out to 5. Or did I screw that up? 1, 2, whoops, I can't count. 1, 2, 3. So was this one good? This one, oh, this amplitude ain't right on part D, so it's part A. And then this is more of the same. Okay, so here is a application problem. Tell us transfer. This is one I just did. So this is the North Dakota one. Here's a weird helicopter one. So you got a picture going here, and then there's an angle of depression. Get to use that phrase. Okay, so here's kind of the horizontal, and then they give us this angle of depression is 34 degrees, and the helicopter is at 1,050 feet. And they want to probably know this distance across the river. Okay, so as the helicopter is hovering 1,050 feet above the small island, the figure shows the angle of depression. How far off the coast to the nearest foot is the island? Okay, so we flew to the island. Okay, so this angle in here is just going to be 90 minus 34. Which I refuse to do in my head, apparently, which is 56 degrees. And then we could go, all right, tan of 56 is equal to opposite, which is D, all over adjacent, which is 1050. And then your answer is just going to be 1050 tan 56, whatever that is. Let's look at the next one. Is that it? Did I do them all? No. Okay, so there's a weird hot air balloon problem. It's kind of a double triangle scenario. Okay, sure. We have this is kind of our x that we're trying to figure out. We have two angles given, 30.7 degrees and then 15.8 degrees. And they're telling us this distance is 124 feet. Okay, and it's a right triangle. Okay, and apparently there's a hot air balloon. Starts off right here and then ends up right here. Okay. So the hot air balloon is rising vertically. The angle of elevation from some person on the ground, apparently this person's watching and it's changing over time. It changes from 15.8 degrees to 30.7 degrees, and then they want to know how far to the nearest tenth of a foot is the balloon rising during this period. So again, I think we can kind of play it as two different triangles with two different opposite sides. So you have this side A, and then you have this other side here, B, and then you could define X to be A minus B. Okay. And then you could say, all right, A, you could say tan of 15.8 degrees is equal to opposite, which is B, all over adjacent, which is 124. Then solve for B, and then you can say tan of 30.7 degrees is opposite, which is A, all over adjacent, which is again 124. And then solve for A and B, and then plop those into this A minus B formula, and you'd have your answer. Okay, so let's leave it at that, and we'll see you next time.